Okay, so in this video we're going to introduce something called the Pell equation, which is a famous Diophantine equation. So Diophantine equation being an equation where you need integer solutions to the equation. So this Diophantine equation is so it's supposed to be a motivation for us to study a structure a mathematical object that tells us a lot about the structure of algebraic numbers, and this is called an extension field, or a field extension, or maybe an integer extension, or a ring extension. Well, anyway, an extension of the rationals to include a algebraic number, and maybe the extension of the integers to include an algebraic number. And we will show that if by adding an algebraic number to maybe q, and then considering the smallest such set that contains the algebraic number, that is still a field, just like q is a field. A field being that we can do addition, multiplication, division by non-zero elements. And that in Z we can do addition, subtraction, multiplication, but we can't do division. And it's the same is true with Z when we add an algebraic number and just have it closed into addition and multiplication. So if you haven't heard of closure in addition and multiplication, that will be explained in more detail. But first, we're going to have a look at the Pell equation. So Pell equation is an equation in the form a squared plus k b squared equals 1. And we want integer solutions for a and b. So an example would be, let's see, so if k equals 2, which is basically the thing we'll consider, and most of the look we have, because it's a bit strange way to say it, but it turns out, and you can have a look at it yourself. It's not difficult to show that for this should be a negative sign. That for positive, for negative values of k, the solutions of this equation with integer solutions of this equation is very, very straightforward. For k equals 0, it's also straightforward. A is plus or minus 1. For k equals 1, it's also straightforward because you can apply the difference of two squares. But for positive k, it's not quite so straightforward, and that's why we'll bring in some algebraic numbers to see what we can do. So let's have a look at k equals 2, which is actually the first not so simple case. So k equals 2. So I want you to try and see if you can find some a and b for which this is satisfied, integer a and b, so whole numbers. So let's have a look. So maybe one obvious one is, maybe not obvious, but 2, 1. So that is a equals 2 and b equals 1. Is that right? No, it's not. No. What am I doing? No, sorry, my bad. It's a equals 3, and b equals 2. Let's just check this works. I'm sorry. Anyway, so a cubed, a squared equals 9, and b squared And this is, sorry, this is a squared. What am I doing? Okay, a squared plus b squared equals 2 squared, which is 4. And then we have that a squared plus minus 2b squared is 9 minus 2 times 4. Oh dear, 2 times 4, and this is equal to 1, as we want to take. And we want to find all such numbers. Okay, and this is as far as we'll go in this video. So in the next video, we'll actually we'll explore this in more detail, right? With algebraic numbers. And you might, if you know, what do you call it, difference of two squares, you might actually see how we can actually look at this, what we can do to this, using a difference of two squares and using algebraic numbers. Yeah, so see you in the next video.